Right now, inside a pregnant woman's body, somewhere in the world, an embryo is growing a tail. It is small. It has vertebrae. It looks, for a few weeks, exactly like the tail of any other mammal on Earth. Then it disappears. By the time that baby is born, there is no tail left. Just a small, unremarkable bone at the base of the spine. Most people never think about it. Most people don't even know it's there. But that bone is a fossil. Not a fossil in rock. A fossil in your body. It is the leftover of something your ancestors used to have, used to need, and then, about 25 million years ago, stopped growing altogether. So what happened? Why did an entire lineage of primates, the lineage that eventually became gorillas, chimpanzees, orangutans, and you, give up one of the most useful pieces of anatomy in the animal kingdom? The answer is stranger than you'd expect. And it starts not with humans, but with a monkey swinging through the trees. Tails in most primates are not decorative. They are essential. A monkey moving through a forest canopy uses its tail as a fifth limb. For balance, for grip, sometimes even for hanging from a branch while both hands are busy. In some New World monkeys, the tail is prehensile, meaning it can grasp, almost like a hand. So losing a tail should be a disadvantage. And for millions of years, it was never lost. Every early primate had one. Then something changed in the lineage that would eventually lead to apes and humans. Around 25 million years ago, the ancestors of what scientists call hominoids, the group that includes gibbons, orangutans, gorillas, chimpanzees, and humans, stopped growing tails entirely. Not shorter tails. No tails. This wasn't a slow fade. It was closer to a switch being flipped. For decades, the leading explanation was about movement. Ape ancestors were getting larger, and they were starting to move differently through the trees. Not running along branches like a monkey, but swinging beneath them, using their arms. This style of movement is called brachiation. If you've ever watched a gibbon cross a forest canopy hand over hand, you've seen it in its purest form. The idea was simple. If you're hanging below a branch instead of running on top of it, a tail stops being useful for balance. Evolution doesn't keep expensive traits around once they stop paying for themselves. A tail takes energy to grow, energy to move, energy to maintain. If it isn't earning its cost, natural selection quietly starts removing it. That explanation held for a long time. It made sense. It fit the fossil record reasonably well, but it left one enormous question unanswered. How? Not why. How? What actually happens biologically to erase a tail from a developing embryo? Evolution doesn't just decide something, it has to work through genes, through DNA, through the actual machinery of how a body is built. That question sat mostly unsolved until 2021, when a geneticist named Bozia, working out of NYU's Grossman School of Medicine, decided to look for the switch itself. Zia's approach was almost deceptively simple. If humans and apes lost their tails, and monkeys didn't, then somewhere in the genome there should be a difference, a specific stretch of DNA that behaves differently in tailless primates than in tailed ones. So his team compared the genomes of tailed and tailless primates gene by gene, looking for anything that stood out. They found it in a gene called TBXT, a gene long known to be involved in tail development across many species, from mice to fish to reptiles. But the mutation wasn't in the gene itself. It was hiding in what scientists call a non-coding region, a stretch of DNA that doesn't build proteins directly, but controls how nearby genes are switched on or off. Think of it less like a broken part and more like a corrupted instruction sitting right next to a perfectly good one. Specifically, the researchers found something called an ALU element, a short, repetitive piece of DNA that had inserted itself into the TBXT gene region in the ancestor of all apes and humans. And it hadn't inserted just once, it had inserted twice, in a way that changed how the gene's instructions were read. To test whether this mutation actually caused tail loss, Zia's team did something remarkable. They engineered mice to carry the same genetic change found in ape ancestors. The mice were born with no tails, or in some cases, very short, stunted ones. That was the moment the theory moved from correlation to something much closer to proof. A single genetic event, tens of millions of years ago, appears to have flipped off tail growth in the ancestors of every ape and every human alive today. But here's where the story gets more complicated and more interesting. The same mutation that removed the tail also seemed to come with a cost. In the engineered mice, researchers noticed something else: a higher rate of neural tube defects.